Welcome to Enterprise Deep Learning with DL4j. And she might want to, she thinks she's taking a phone call. We'll wait. It's cool. I'm teasing. I don't care. I'm not. You are in a technical presentation. I'm Josh Patterson. This is Hadoop Summit, if you're lost. And we're going to talk about deep learning and some practical integrations with the modern data processing frameworks, Hadoop and Spark. Who am I? A little bit about me. A long time ago, I used to do mesh and swarm algorithms, and then I wanted to actually get paid, so I stopped doing that. And I went to the smart grid because I had sensor network experience, and we did a bunch of sensor collection stuff and gambled on Hadoop, and that went okay. And then I went to Cloudera and that for a little startup, and they did all right. So I've been very fortunate in that tract. I guess you'd call that IoT now, maybe? What do they call it? I don't know. But today I have a small consultancy within the Hadoop space, the machine learning space, and I also am a committer and work on the architecture of DL4j suite and help out SkyMind wherever I can. So what are we going to talk about today? Let's kick it off. What's deep learning? Who knows what deep learning is? Everybody. You guys have been reading VentureBeat, right? Teasing. You read all the good papers. What's DL4j? And then let's talk about some practical ways to actually use it. Who's actually using deep learning in production today? Yeah, that's the tough part. It's kind of like, that guy raised his hand. I'm going to give him a hard time. No, it's kind of like Hadoop in like 2010. It's just like everybody wanted to talk about it, but nobody's actually using it. And maybe some other technologies I won't pick on today, but I can pick on Hadoop because I used to work at Cloudera. So yeah, it needs to get easier, and that's what we're going to talk about today to make it more practical. So what's deep learning? Well, anybody ever seen MNIST? MNIST data set? Yeah? It's basically handwritten digits, and they've been pre-processed a little bit. Jan LeCun has this data set you can download. Jan LeCun is a very, very famous machine learning researcher, now runs the Facebook lab. It's a very hard nonlinear problem. And in the image analysis space, classifying digits is tough. And what we did over the years is we began to try these ways to automate feature engineering. Who's done feature engineering? Yeah. So what you do is you basically take the raw bits and then you extract pieces of them, in layman's term, to create a vector that is more learnable in a training data set. And there's all sorts of tricks to do in there. In the time series realm, I used to use a low-pass filter called SAX by Iman Keogh at UCR, really brilliant guy in the time series domain. These techniques have been around for years, and over time, they began to get wrapped up into workflows. And as Jan LeCun says, we're just looking to build machines that can represent the world. Feature creation can be very time-consuming, like in machine learning, collecting data, knowing data, understanding data, measuring data, visualizing data, building features. That's hard, time-consuming. How do we make that easier? That's what I want to talk about today. So, but deep learning itself it's a collection of old concepts put back together in new ways to get a little bit better. Who thinks deep learning is artificial intelligence? Oh, you guys are good. I like you guys already. Yeah, anybody who says it's AI or they've hit AI, my threshold is if HAL from 2001 blew you out of an airlock at an inopportune time, you've hit AI. Until then, it's just like classification regression. So one of the cool things I love about deep learning was, I did a lot of work with logistic regression, if you've seen some of my old talks. You could visualize what it was thinking about. Logistic regression, you just go look at the parameter vector and you're just like, that's a bunch of floating point numbers. I'm going to go to sleep now. But here, if you visualize what's called the activations, which is the hidden neurons, you can do some cool tricks. You begin to see, as we're learning MNIST, it's like the static TV, a bunch of static TVs, and all of a sudden things begin to emerge, and then features begin to emerge. Automated feature engineering. with the restricted Boltzmann. This is rendering what's called a restricted Boltzmann machine, which is a chunk of a deep belief network. The first time I saw this, I was like, this is a very different thing and is very powerful. I don't know what's going on there, but I need to know more. And I started reading some of Jeff Dean's papers because, you know, copying what Jeff Dean is doing 3 years later tends to be a pretty good pattern. It works out pretty good for people. Doug Cutting did okay with that. So if you look there, you can see part of a 7, right? You see a chunk of a feature. And we didn't do any like, oh, I think a 7 is there. The machine did it for us. That's pretty cool. And if we could pass those features up to higher level restricted layers, then we could learn more complicated nonlinear features, learn chunks of features, and then put them together higher. And that's what a deep belief network is. That lower level, you put the input image in, it learns to represent the image, the input data, and then it passes those features up, and at the end, it can put all the features together. And if you want to go read a lot of math, which I'm not a fan of in these type presentations, check out Jan LeCun or Hinton. They have, or Yashio Bengio, they have great fundamentals of what's going on here. So there's 4 major deep learning architectures. There's deep belief networks, which are layers of restricted Boltzmann machines which learn those features in an unsupervised manner, and then they pass those weights over as like a great idea to a canonical feed-forward network, and they say, okay, start here, now go do your learning at this great starting place and fine-tune it. So you have a pre-train and then a fine-tune pass, right? A lot of machinery going in there with loss functions and stuff like that. The next one would be convolutional networks as an architecture. Jan LeCun is very famous for this. Who's heard of convolutional? If you've seen the image, basically convolutional will destroy all the image competitions. All the startups who are doing really cool imaging stuff use convolutional. And Jan LeCun is very famous for making them do, as Hinton will say, Jan LeCun can make them do anything. Recurrent networks are really interesting in time series, and then recursive. Have you ever seen where they break down the image and they put labels all over stuff? Right there, that's interesting. So that's what it is at a high level. And you can go dig into it and find all the math and make sure the proofs work on your own time. I'm gonna leave that as your homework for tonight on the plane ride home. How do we actually make it usable? There's a lot of theory out there, and there's always really cool stuff, but you go look at it, and then it's like, I can't integrate this in anything. And so that was something we came up with DL4j. Me and Adam Gibson, I met him about 2 years ago, and we started working on this stuff. And he said, I have some restricted Boltzmann machines. I want to build a deep belief network. And I was like, all right, well, I think we should do it on the JVM because I want to put it on Hadoop with some parallel iterative mindsets. He's like, all right, well, we'll do that. And we caught some flack for that. I think Yashio Bengio said we were terrible people or something. I don't know. It's in Wired. But, and I was like, he's like, well, I want to make it accessible with Scala and Python. And I was like, all right, you do that, but we'll make it SL2 license. So I wanted to make it look like what we had learned was successful pieces of Hadoop. And I started working on the parallelization stuff and borrowed some parallel iterative ideas with parameter averaging. I want to go deep into that today. And then we made a Yarn version, and then Spark got more integrated in Hadoop, and we made a Spark version. And I was like, parameter averaging is just a concept. So let's be runtime neutral. Let's run local. Let's run on Hadoop. Let's run on Spark. Let's run on AWS. Same engine. What's the problem with like R? It's a serial-based, online learning machine. It doesn't parallelize very, very well. I love Revolution, but that's always been a problem with it. And so I said, let's build a more modern architecture so that the same engine runs everywhere and it uses the same model everywhere. And that's going to behoove us down the road. 2 years later, the fruits of our labor are out there on GitHub. Got over 1,000 stars, which in GitHub parlance is pretty good. What are some issues in machine learning that we wanted to fight? Because I spent a lot of time with Cloudera in the field and with my own company hitting things. One of the major things that you'll see in terms of where workload can live is data gravity. And that's based around, once the data lands somewhere, it begins to suck all the processing to it because you don't want to move data. You move a gigabyte, no big deal. You move a half a terabyte, you move multi-terabytes, so we're starting to get into some friction, the coefficient of friction. And so I begin to notice, everybody at this conference now, all their tools run native on Hadoop, 4 years ago, that wasn't the case, this conference. The vendors looked very different at Hadoop World and Hadoop Summit. Somebody asked me to define big data one time, which I don't like the term, and I don't like cloud, and I don't like smart grid, because I'm grouchy. But if you have to move the data, you don't have before you process it, you don't have big data. That's my role. Throw rocks, but that's my role. And so I wanted to, runtime neutral was very interesting because I wanted things to play nicely on Yarn or AWS. And I wanted to be able to sit on top of that. Like same way a map task can sit on top of a data block and operate at the transfer rate of disk. I wanted our same style processing with Jeff Dean's architecture. We did the same thing. And we've talked to some engineers over there and got some tips on what to do there. Integration issues. Who's ever dealt with integration issues? If everyone in this room doesn't raise their hand, I'm just going to walk out. Now, I never forget one time I was working with an insurance company up north, and they said, okay, we have Hadoop. I was like, great. And they're like, okay, let's do some machine learning. I was like, okay. I was like, what do you want to do? And they're like, well, let's classify some tweets. Because that's the best use case of all time, right? Most useful? No, that's terrible. I love Twitter. Tweets are kind of, it's a great baby use case. I was like, all right, do TF-IDF on the tweets, right? TF-IDF, that's how you build, you basically take all this unbounded text and you make a parameter, make a vector of a certain size. Hard stop in the room. What's TF-IDF? I was like, yeah. And I was like, well, let's go read a paper, or here's a book, and they're like, no, we need a tool. So it very became, they could sort of ingest. They were learning to do some Hive, to do some ETL, right? Vectorization was off the table. We're talking baby text. We're not talking images and audio, which is all the promises of every, right? Hadoop is, we're going to ingest your video, your audio, and then we're going to do cool things with it, right? Well, how do you convert that into something you can use? Vendors don't like to talk about that. I'm not a vendor today, so I can be the right blanket until they throw me out, because the guys who are paying are not going to like that story. Anyway, most ML tools historically have their own input formats kind of tied to it. I hate that. I hated how Mahout did it. I hated how all the tools did it. And I was like, the Unix principle is like you break these things apart and make them interconnect, right? The old Unix principle. We don't do that. Why not? Machine learning needs to grow up, and it needs to be runtime neutral. It needs to operate where the data is, but these pieces have to get more mature. These legacy architectures have to get better if this stuff is ever going to go in production, because, guys, quite honestly, I also, my Patterson consulting side, I advise certain large companies on what they need to do. Sometimes I actually help them do it. Sometimes I actually advise them what they need to do, and I review people's pitches to them. Most companies don't have a great take on the use cases. It's always, what question do I have Hadoop? What question do I ask? Not how do I do it? It's like, and then the how. It's the why. What's its worth? And then find some stakeholders who actually put some weight behind it, so you'll have the budget to do it. And then the how really get back down. That's why these use cases are having so much trouble. And I actually had to write this position report on them recently. I was just like, the state of machine learning in 2015. And one of the, I boiled it down to, I was like, why do people still chase this if we've had so much trouble with it? It's because we want to be Google, we want to be Amazon, we want to be Facebook. What are the really cool use cases? Automated image tagging at Facebook, automated recommendation at Amazon, and dug into how those worked. Just throwing a couple components, at something doesn't today have the integration factor that it needs to go to production. Going to production on Hadoop is tough. I love Hadoop, but it's tough. Legacy architectures have to get updated. So how do we do that? That's where DL4j, the impetus. We have 4 major pieces in the DL4j. It's a suite of tools. Like Hadoop is not really just HDFS. It's MapReduce, it's HDFS, Zookeeper, it's HBase. And those at the beginning were just like HDFS, MapReduce, and Hive. And they just kept adding pieces, and then a distro wrapped together, a fingerprint. Horton and Cloudera, as much as they hate to admit this, are really similar in terms of their fingerprint. It's really just Ambari versus Cloudera Manager is the difference. But the fingerprint is the different part, and the fingerprint is how you tie it in. Same thing here. Today in our suite, DL4j is a core modeling library. Canova begins to talk to all those different sources that you want to vectorize. DL4j allows you to separate how you do your linear algebra computations with swappable backends. And then Arbor separates out the model evaluation, things like tenfold cross-validation and RLC curves. By the way, Adam just gave an amazing talk on DL4j at Scala Days, and that's why he's not here today. He's over in Amsterdam. And so we get to enterprise-grade deep learning. And Spark's thrown in. I'm not going to talk a lot about Spark. There's plenty of other talks here that you guys have already. You guys know Spark? You got Spark. Okay. So this is really what's happening. This is the pattern. Traditional online learning over here. See training sample and like stochastic gradient descent, update the parameter vector. See the next one, update the parameter vector. Parallelizing that, you split up the data sets. You have workers work on each data set, and every so often you take all those partial models and you put them together, and then you send them back to the workers and you say, keep going. And there's different ways to find a terminating condition. The one on the right side is more complicated. If you want to take a look, and if you've seen any of my parallel iterative talks before, linear regression, logistic regression, plain neural nets, I want to show this slide. If you look at Jeff Dean's work, same thing. Alex Smolla has done a lot in this area. And then John Langford is the godfather of Valpal Rabbit. Same concept, slightly different wrinkles. But that's what's going on under the hood with Yarn or with Spark. This is what the API looks like for DL4j on Spark with GPUs. I threw those in because I like you guys. So you can't really read it on the screen very well because I want to get the whole thing in there. At the top, you pretty much say we're using Spark. And then there is a multi-layer configuration. That's common to all DL4j networks. And then you can set all the parameters, momentum, loss functions, stuff like that. And then at the bottom, it just basically says, here you go, Spark, go. And the cool thing is, a serial version of this, the API, looks very similar, not a different engine. And so the models that are computed over in Spark with parameter averaging are interoperable with the models that you compute elsewhere. API level things are for early adopters. Who still does their parallel programming at the Java API level? Any MapReduce programmers left in the world? Hey, I like you. It's like 5% of us left. I used to do a ton of that. Spark API, Java, Scala? A little bit more? How many of you guys are in production? I'm picking on you. So API is for early adopters. You know, what happened to the MapReduce people? We came along, and then everybody decided at the bank side, we don't want to do MapReduce Java API. We want to do Hive. Higher level languages, make things easier, democratize the power of Hadoop, of MapReduce, make this easier. And so that's what we, that's where the next place me and Adam pushed to go. By the way, the easiest way to enable, like I talked about with DL4j, you just change the Maven dependency. You don't change any math, and you can go from local NBLOS or matrix computations on the local CPU or the local GPU to work seamlessly with Spark or local just by changing that Maven dependency. That's really handy. You're not rewriting anything. And that's all Adam, by the way. He does all the back-end matrix stuff. That's not my land. So what do we really want? Okay, we've gone low. We've looked at Spark. We looked at API. That's great. We can dig into that. That's the early adopter stuff. Let's make it easier. I came out of the gate talking about we need to make things more productionizable. We need to be able to take that raw audio data, right? Because deep learning is so amazing on audio, so amazing on images. Who's actually done hand decomposition of like audio or image data into vectors before? 1, 2, yeah, 0.5%. It's horrible. I wrote MNIST parsing code. Shoot me. It's just sunk costs, and the best you can do is not mess it up. We want to get that extracted into some sort of vector format. You shouldn't really do, just like you shouldn't be writing input formats in Hadoop. You should just be working in your algorithm. Model the data, evaluate the data. Traditionally, a lot of tools tie these all together. And if that tool doesn't fit what you're working on, you're kind of out of luck, right? The DL4j suite of tools has a more progressive way of looking at this. Click. So what do you do when you get a new tool? You model iris, right? You go over to the UCI repository, and it's like taking a bazooka to hit like an ant with deep learning and iris. But I want to make an example I can talk about as opposed to showing other code. We need to vectorize the data, so let's use Canova. And we may want to do some transforms, because the UCI data, it's in CSV format, right? It's not in vectorized format. It's not arrays of floating point numbers. So we'll be good. Then we want to build a model over this data. We need to transform it into some intermediate representation. We're going to model it, and then we want to see how well we modeled. Tenfold cross-validation is a great way to do that. So Canova, let's double-click on that for a second. It's a library of tools to take audio, video, image, text, CSV data, and use input formats like you do with Hadoop. Same concept. And they're just smart enough to say this is local data, or this is HDFS data, or this is split. And spew those up as key value pairs and then run them through the transformation pipeline. It's open source. It's part of the DL4j suite. And today we have the CLI stuff, workflows, are all part of the next release. API stuff is in there currently, but as part of some things I'll talk about here in a second. In about a month, we're going to bake this and completely release this. But you can go look in GitHub right now and check out the commits and be like, okay, that's where that branch is at. So right now, you can do like CSV transforms. So to take you through this, vectorization with Canova, you set up a configuration file. You select an input format and output format. We'll talk about how that plays together. And then a scheme on how you want to vectorize things. And then for this particular one, I'm going to spit out SVM Lite. Who's heard of SVM Lite? Yeah, so like that's an older format that a tool, I forget which tool it's called, it uses. But it's basically a text way to represent vectors. But once you get it in that intermediate format, image, audio, what have you, any tool that has an input format for SVM Lite can use it, right? So you set up all that configuration file. And this is generally, it's just a properties file. This is a subset of it. There's some other commands in here. But if you go look at input.format, line input format, you've seen stuff like that before. Input directory, where's the raw iris data from UCI? And then what kind of vector schema are we going to impose over it? Well, what's a vector schema? So what happens when you get data in that's raw in CSV format? You may want some columns, you may not want some columns, and some columns may need to be normalized or binarized or what have you. You need to transform them, and you need to spit them out in a way that actually can be modeled. Or if they have labels in them, you need to index those labels. This is time-consuming work that I hate, for my customers, they hate. You shouldn't mess with it. This is what the iris Canova vector schema looks like. Pretty simple, right? And it's based really, really close to our schema stuff. I just ripped it off and added a transform column. That's baked in there right now. You just say delimiter is this. Works pretty good. So what does this look like in practice? You type Canova space vectorize, like you type Hadoop space, jar or Hadoop space fs-ls. Same concept. We're going back to the command line interface. Why Bash? Why not the API? Because Bash is the largest imprint in the world. It's not Python. It's not Scala. We do have those interfaces, and I'm not talking about those today. That's Adam's talk. He can talk about Scala's type, stuff all he wants. But I wanted it just for like the practitioner who didn't want to mess with stuff. He just wants to take raw audio and then model it over and over again until he finds the right pattern or she finds the right pattern, and then evaluate it. Right? 3 steps, 3 sets of commands, tools that you recognize, and an API that's very friendly. Be integrated. The next thing will be to make this an Uzi workflow, because all of these tools are Yarn aware, and they'll be first-class citizens. So you could go into your UI of choice and kick off this workflow as a Yarn job on Hadoop on top of the data, or you can do it locally. So this is, I'm going to put my SkyMine advisor hat on for a second. Just as Red Hat was to Linux, and just as Cloudera and Horton, since this is a Horton conference, I'll give them a nod there, are to Hadoop. SkyMine is DL4j. SkyMine produces RPMs, just like if we packaged up, Hadoop back in the day and applied some patches to DL4j. DL4j has its own entity as an open source tool. If this was interesting, in October, editors willing, we will be releasing a deep learning book, similar content, more workflows, more examples, more practical, hopefully, examples for you guys to take into production. And it's our work with O'Reilly. With that, I appreciate your time and open it for questions. No questions? I didn't do that good. Come on.
Besides deep learning neural networks, what other kind of, I think you said it's a suite of tools. Is there other
There's the four major architectures. We could do like logistic regression because that's built in. But there's other tools that have done that. I've done this work. The parallelization work was pulled out of my old metronome project. It's another open source tool, but this is more baked in to be productionized. We could. Right now, we're just trying to get really good at what we start to do. I mean, there's a lot of things to get right here, not just beyond getting stochastic gradient descent to work or LBFGS to work, but making it work on Hadoop, making the CLI work as promised, making it Uzi compatible, making Canova really be the Rosetta Stone of vectorization. So that's where our focus is. I would say in another year, Adam will that would probably be on his side of the house. He'll probably throw some cycles at some more general tools.
talk a little bit about maybe hardware, computation time, and various types of problems, scale and problems you can solve?
I'll say this. There are a couple large companies that can't be named for various reasons, business-wise, SkyMine's relationship with them. One of them is doing Spark with multiple GPUs. I say Adam has worked a lot on this. He's treating multiple GPUs on a host like Hadoop treats disks, and then round robins the work across. And that's really amazing. We don't have timings yet because we're trying to bake this thing for the big release to go out with the book in the fall. But there's a lot of image stuff, some fraud analysis. Anybody who does convolutional is really interested in images, fraud detection, anomaly detection. But this library is built to be pretty much go after all of those. Make deep learning more practical to the Fortune 500. And anything you've seen published as a use case, we're either probably touching or set up to do. We're thinking about doing, obviously, as you can see with the Canova work, with the audio input formats and the image input formats. We want to make those use cases. I'm not going to pretend that they're 100% ready to roll into production, but we're going to make them a lot closer than where they were. Because I've been on a lot of bespoke engagements where you end up writing a lot of that glue code that we're trying to just get away, close the gap. It's a combination of two things. I would say, Chris, you got any numbers you want to throw out? He's asking what's the largest data set we've learned against. Stuff like that. The thing is, when you're constantly trying to build a tool that it's both disk bound and CPU bound, and GPUs, CPUs, and disk, we're constantly going, oh, that needs to be fixed, that needs to be updated, coming over here. Pushing it up into the multi-terabytes, we hadn't got there yet. But it's built to sit in Hadoop to do that when we get there. I think that's the most fair way to say it.
Explain how to deploy those models.
Say again?
How to deploy the model.
Yeah, deploying the models. So like that's the other thing. It's like once you build a model, let's say you want to score transactions for fraud, right? Once you build a model, you like it. One of the things I'm going to add in there is basically a Spark and a MapReduce job that scans across the data set, and it has like the Canova will take the raw data, turn it into a vector, and then apply the model. We might make another component to do that, or just put that as DL4j. But yes, deployment of models in a runtime agnostic sense is part of it. So one thing you'll see very popular in architectures, I hate the term real time, but real time usually means as things stream by, we just do something really quick with it, and then it goes on back to the batch system. You build the model in the batch system, and then you deploy it over to Storm, right, or Kafka, or whatever the popular thing is today. And as it comes by, just hit it, just vectorize it real quickly, and hopefully you don't have to, hopefully you can do it with just that record. I have one customer who detects fraud they actually use Valpal Wabbit in Storm. Hopefully I can say that. They've talked about it before. And do that. They build the model over here, and they deploy it. So we'll add some bindings for whichever streaming frameworks are requested, and then we'll also do batch deployment where you get pulled up in something that's a single scan over across a large amount of data. Because batch is your base case. I know everyone wants to talk about real time. Batch is where you start, and then you end up making your response thresholds shorter and shorter and shorter until you get to a streaming thing. And so we want to, batch is always where I start from a practical sense. Does that answer your question?
I actually want to know the whole picture, how the deep learning do.
Come see me. I'll draw. I'm working on that. As we build out Canova, it's a very, it has high goals. Vectorize everything, make it simple. Like right now, you can do text with TF out EF, and it's boom, it's this configuration, spit it out. You can do MNIST, spit out SVM Lite. You can do raw images and spit out SVM Lite. The next thing I want to add is the ability to do pipeline post-processors, and then just take that raw array of floating point numbers, and then you just add your transforms on top of it, and then just do like a down sampling, and then like a binarized layer like that. Each pathway I've made specific so far because text processing for vectorization ends up being typically different than CSV and image. Maybe down the road we unify those pipelines, but that's transparent to you. But those post-processors are what we're working on probably for release 2, probably Q1 2016, Q4 2015. Does that answer your question?
If you do text, can you do rule-based as well?
Can you do what?
Rule-based.
Can you give me an example?
Let's say for tweets, I say for
I'd probably put that in ETL phase. You've got to be really disciplined in what phase. Today's pipelines, and I've spent a lot of time with this, is you need your ingest phase. You need to connect to your data source and ingest, and then you land it somewhere. And then you do some raw ETL. Data prep is actually in there. Trifacta is doing phenomenal work in the data prep stage. I'd probably use a tool like Trifacta, spit that out, and then vectorize it with Canova. I think your workflow will be better. You could do some filtering in Canova, but right now I just don't think that's the place for it. Yeah. So that's admittedly right now that's evolving. We're adding in the text pipeline, like vectorization is a really wide topic, and it's pretty terrible, and it makes me very grumpy. And that's why I take my big rubber mallet and I look for things that make me the most grumpy, and as a younger programmer, like Adam is like 24, and so things he gets really excited. I call him the refactor squirrel, and he runs around and he's like in the middle of the night he'll refactor everything I did the previous day. You know, but I find things that make me, because I'm an older programmer, I find things that make me grumpy, and I hit him with a mallet. So things like that, like image vectorization, makes me angry. You know, like TF-IDF. I mean, who wants to rewrite that? I mean, how can you do it better than people who've done it before? And so you bake that in, and you basically say text, and then I want to use that post-processor. And so that type stuff is baked in. So if you had like a specific flavor of it, you should just like make that a, you know, request and on the project, and I'll put it on the queue. Yeah. Let me make sure I don't mangle this. You're moving the workers to the data, because in a big data place, like I said, my principle is, my rule for big data is if you ever move the data, you don't have big data. So I'm moving the worker to sit on top of it. They build a partial model on top of that disk. That core sits on top of that spindle. You operate at the transfer rate of the spindle, so you can maximize the throughput, and then it sends that partial model up to the master worker, which stays resident, parameter averages, and then sends it back. Right. So that would be the parameter server at Google. We've discussed that with them. I've sat down with Dr. Alex Mullen, and we've talked about different strategies for the parameter server. If you guys, when you guys hit like a multi-billion parameter size, that's when we'll do the work to add that. Right now, people aren't hitting, you know, your use cases are just not hitting that yet. Go ahead, Sunil. There's some ongoing work, yeah. It's just, it's down the queue right now in terms of limitations we're hitting. Is that it? No more? Thanks, guys.